ECE Department Colloquium. It's my pleasure to introduce our speaker today, Dr. Hamed Rahmani. He is going to talk about his very exciting work in developing new wireless powered solutions and the applications that they have in the medical field and also IoT. His background is in electrical engineering. His PhD was from UCLA, where he worked with Aydin Babakhani, one of the top RF groups in the country. Also, he was at Rice before that in Houston, Texas, and before that he received his BS from Sharif University of Technology in Iran in 2014. Currently, he is in the Boston area where he works at Qualcomm as a senior RF integrated circuit design engineer. He's working on a lot of exciting solutions for advanced 5G transmitters and applications they have in the cellular domain. He does a lot of very interesting research spanning all the way from microwave and RFICs to also healthcare applications like biomedical sensing and also high-speed wireless communication and IoT. He's received many awards, including the Texas Instruments Distinguished Fellowship and also the MTTS Graduate Fellowship for Medical Applications. So he's doing a lot of interesting, great work, and very excited to have him explain it. So without further ado, I will introduce him. So if he was here in person, we would all clap for him and welcome him. But today, let's just welcome him virtually, and hopefully one day in the not too distant future, we can have him visit us on campus. So just one thing, please save your questions for the end. And if you do have questions, that's great. I will ask you to raise your hand using the Zoom function, and then we will unmute you to allow you to ask your question. So thank you, and let's welcome Dr. Rahmani.
Well, thank you, Mehdi, for the very kind introduction, and good morning, everyone. It is my pleasure to be here with you virtually and talk about my work on integrated wirelessly powered solutions for medical implants and IoT. At the beginning, just let's evaluate why we are interested in the applications of bioelectronics in the field of medical implants. Well, a few examples of the current applications of wearable technology and implantable technology are shown in this slide, where you can see many wearable and implants are using for a wide range of purposes, from sensing, monitoring, and even stimulation. But this is not the end of the story, and the future of the bioelectronics and biomedical implants field is believed to be based on the development of a closed-loop therapeutic system. In a closed-loop therapeutic system, biomarkers and electrical signals are recorded from the close proximity of a specific organ inside the human body. And after recording, they are processed in real time. And by processing in real time, we can basically come up with the proper therapy and prescribe that therapy in the form of modulating neuron signals and that specific organ inside the body. So you can imagine that this closed loop system will open up an unprecedented opportunity for future medical applications. For example, we can restore and augment the lost psychological functions that have been lost because of the damages to the spinal cord, for example. And also, it can be used to do the drug delivery purpose. Because if you think about it, right now, the chemical drugs are nothing except inducing one specific effect in one specific location of the body. But with the closed loop system, we can exactly do that and eliminate the need for having chemical drugs. But although this application seems very interesting, but unfortunately, the development is severely limited because of the limitations that we are dealing with in the closed loop systems. Neural recording applications are the perfect example to highlight the limitation. And as you can see, a patient is sitting in a protected environment, such as a lab, where because of the presence of these invasive wired connections, patient is exposed to severe infection risk. And of course, he's suffering from mobility discomfort. But in order to close the gap between where we are right now and the requirements of next generation systems, any recording device and any closed loop system should achieve wireless operation and should be able to record electrical signals at a very fine scale in order to guarantee real-time control. Then it means that we need to have a wireless operation, wireless powered, and support high throughput wireless communication as well. And no need to say that any system that we are targeting should be biocompatible and suitable for long-term application. But I'm not claiming that I'm trying to solve the entire problems facing toward the development of a closed loop system. And in fact, not only me, a group of engineers working independently from other researchers across the field cannot achieve this purpose. I want to show a direct quote from NIH Brain Initiative that says, "No single researcher or discovery will solve the brain's mysteries. The most exciting approaches will bridge fields, linking experiment to theory, biology to engineering, tool development to experimental application, human neuroscience to non-human models, and more in innovative ways." So of course, there is still a long way to go and many challenges need to be addressed before we get there. But we want to do our part and we focus on the hardware related challenges and target to develop a distributed sensor network to enable the requirements of next generation implants. A visionary example of such a system is shown here, where you can see that the neural interface is composed of multiple millimeter-sized and integrated systems that are spread all over the brain. The block diagram of one individual cell here is shown here, where you can see we have analog recording and stimulation front end, plus we have a wireless interface that is responsible for conducting wireless communication, plus wireless power delivery. Any system that we are targeting to develop should be able to satisfy the system level requirements that are wireless operation, low power consumption, low cost, and have small form factors in order to realize a scalable system. So in this talk, I am going to focus on the challenges associated for wireless power delivery, wireless connectivity, and finally, analog recording front end that are required for realizing such system, a distributed neural recording. Let's start with the powering and take a look to the current ways that biomedical applications are conducting wireless power delivery. So there are two major categories. Majority of the implants nowadays use battery as the main method for wire-free powering method. And of course, batteries are bulky and large and they have limited lifetime. As a result, they cannot respond to the requirements of long-term and millimeter-sized implants because replacing the battery requires surgery, and that is something certainly we want to avoid. On the other hand, another group of implants use inductive coupling in order to couple electromagnetic energy through a pair of coils. These coils are often centimeter sized and they are operated in tens of megahertz, which again, because of the centimeter size form factor, we are limited in terms of integration. As a remedy to this problem, researchers have been exploring alternative energy sources and energy harvesting solutions in order to come up with a reliable and long-term solution for powering any wireless system. Different energy sources, depending on their need to having an external device for establishing the energy link, can be categorized as intrinsic and external. The intrinsic energy sources are already in the environment and there is no need for any extra device. And few examples can be named as body motion, thermoelectric, and biofuels. But despite these energy sources seems very attractive, unfortunately, they cannot provide high power density and they are not sufficient for biomedical applications specifically. On the other hand, external energy sources can provide sufficient energy density, and examples can be named as electromagnetic waves, ultrasonic, and light. Specifically, I'm interested in electromagnetic waves because of their unique feature that they can pass through bone structures and enable neural recording and stimulation applications. So now that we are fixed on choosing the energy source and wireless power transmission mechanism, then the natural question comes to mind is that at what frequency we want to operate the wireless power transmission system. The choice of frequency is very interesting because we know that as the frequency increases, the size of antennas and the power receiving structures is going to reduce as a result, which is very desirable since we are targeting millimeter-sized form factor. But on the other hand, we know that at a higher frequency, the path loss is also increasing. And keep in mind that this is not a typical communication problem. We are dealing with intervening biological tissues. In fact, here is a very simple model based on a two-port network for a wireless power transmission. And there are different sources for power loss, but most importantly, because the presence of these biological tissues, the problem of wireless power transmission to millimeter-sized implants is very challenging. And the reason is, not only the presence of biological tissues degrade the energy efficiency, but at the same time, biological tissues show some thermal absorption behavior toward electromagnetic waves. Just to provide an example, you see the thermal distribution in tissue composition of human head is simulated at 500 megahertz and 2 gigahertz. Moving from left to right, the thermal absorption almost increases by a factor of 4. So it means that for a specific transmitted power level, we have 4 times more absorption, but at the same time, we are dealing with safety limits and safety regulations. It means that we cannot arbitrarily increase the transmitted power level and deliver as much as power we want on the other side to the millimeter-sized implant. This will introduce a very serious challenge because it limits the power budget that is available for the operation of the system. But this is not the end of the story, and except the safety limits, we are also dealing with some other undesirable factors from sensitivity to the composition of the link, the misalignment of the antennas, and the movement that is inevitable for practical cases. And also, we are dealing with another subset of challenges that are coming from the circuits that are required for converting incoming RF signal into the DC voltage for operation of the system. Long story short, it means that there is a specific limit on the amount of power we can harvest. And we did an extensive research and we concluded that depending on the operating region of the electromagnetic fields and the antennas that you are using for power delivery, either it is a medical application or an IoT application, the amount of power that can be harvested by a millimeter-sized on-chip system is limited to 100 microwatt for the case of near field. And the situation gets even worse if you go to higher frequencies and higher operating distance. You are limited to 10 microwatt. So take a moment here. We are having only 100 microwatt, and we want to design a system that includes a radio that supports tens of megabit per second. How on earth we can manage to use this 100 microwatt and realize that kind of radio? Here is the block diagram of the system that we are targeting. You see we have the power harvesting system and the transmitter and the receiver. But in order to answer that question, I want to focus your attention on one example of an oldest power management unit that has been already out there. The example of a water mill is a perfect scenario in order to show how the concept of power management unit can be adopted for electrical circuits. Here, if the water flow is not strong enough for having a continuous rotation in the water mill, what will happen is that this water flow accumulates over these buckets, and once the power is enough, it induces a rotation until it stops. The exact same concept can be applied here. If the energy is coming through an external wireless link and is picked up by this rectangle, it is converted into a DC voltage, and there's a power management unit here that turns off the power demanding blocks, in our case, the data transmitter. Since the power flow into the system is larger than the consumed power in the system, then the energy accumulates over this storage capacitor and the voltage rises until we hit a predefined high threshold value. Once we hit this level, the PMU activates the data transmitter, and since we are consuming more power, the voltage rapidly drops until we hit a low threshold predefined value, and this operation continues over the time. But going back to the example of the water, what will happen if the power flow into the system is enough in order to guarantee a continuous operation? Then no problem. In this case, PMU sets the voltage across the capacitor to be between VL and VH, and the data communication can be conducted continuously over time. So it seems that now we have a solution in order to drive a power demanding block, such as a data transmitter, using only 100 microwatt of available power. But the next step and the next important question is the design of that transceiver itself. Before going into the circuit details and the design implementation, I want to provide an overview where we started. We said that we want to design a system that is compatible with the wirelessly powered scheme, and we want to have fully on-chip integration, which means no external crystal oscillator for generating accurate frequency whatsoever. And therefore, we want to have the minimal complexity in the design of the transceiver in order to guarantee the minimal power consumption and achieve the highest value of energy efficiency. To do so, we designed the data transceiver with the general scheme that is shown in this slide. You see that there are two antennas, one on-chip coil and one on-chip dipole antenna. The on-chip coil is shared between a power harvesting system and the data receiver, and the power is flowing into the system using an wireless link that operates at variable lots of 250 megahertz. I refer to this wireless link as downlink path during the rest of the presentation. On the other hand, on the transmitter side, we are choosing a frequency close to 4.1 gigahertz. I'm going to talk about why we chose these values in the next slide. And the transmitter uses another dipole antenna in order to come up with the minimal interference between the strong power link and the uplink data communication. So of course, the communication scheme here is based on frequency division duplexing, and we are featuring amplitude-based modulation in order to minimize the complexity of the system and get the minimal power consumption. Why we chose that 250 megahertz and 4.2 gigahertz for the operation of the system? The short answer is we implemented the antennas required for power delivery and data communication in the uplink path as a two-turn square-shaped loop and a modified version of a dipole antenna. Since these antennas have different polarities also, it greatly helps to minimize the mutual effects coupling between the uplink and downlink. And we used a unified electromagnetic configuration in order to simulate the power transfer efficiency from a 2 centimeter by 2 centimeter external power coil to the millimeter-sized on-chip coil. And at the same time, the efficiency in the uplink from the dipole antenna to an ultra-wideband monopole antenna. The wireless link here is simulated assuming different composition for the wireless link, as shown here. And as you can see here, for the power link, choosing 250 megahertz roughly will give us an optimal solution where we have almost minus 20 dB of power transfer efficiency. For the uplink also, it's interesting because we observe that we can get a nearly flat response for the uplink if we operate between 4 to 5 gigahertz. Therefore, the frequency of the uplink also is chosen to fall within this range, and we proceeded with the circuit design. So now that we have covered the power management units and the selection for the frequency, so now it's the time to discuss about the circuit design and the techniques in order to minimize the power consumption. First of all, let's start with the data receiver itself, which is implemented based on an amplitude shift keying modulation. The downlink data stream is incorporated into the wireless power link and is modulating the power carrier with an ASK modulation. In order to not interfere with the power flow to the system, the modulation index should be as small as possible, and we can envision an abstract form for the incoming signal to the system that is described according to this formula, FRF being the power carrier frequency, and M modulation index, and X of T, the baseband data. The data receiver in this work is implemented based on a self-mixing architecture, which is a perfect configuration if we want to have a passive receiver that doesn't consume any active power. In a self-mixing architecture, the same RF signal is used as the local oscillator. And if we do the math and work out the equations, you see that the output voltage of the self-mixer will have a form similar to this equation, where you have some components at DC, some high frequency components, and most importantly, the baseband data itself. Of course, when we are talking about the data receiver, we are interested in the baseband data. So we have to get rid of the DC term and the high frequency terms. To do so, the output of the self-mixer is followed by another averaging filter that has a very low cutoff frequency. As a result, the V average has a very slow transition compared with the V envelope itself. An example is shown here. You can see if we compare these two waveforms and amplify the signal, we can retrieve the original baseband data at the output. This is exactly what we did, And in order to improve the fidelity of the signal and make the system more immune to the noise, we also followed the comparator by another Schmidt trigger circuit, so we can guarantee a very high reliable performance for the data receiver. And finally, and the most important part of the system is the data transmitter itself. The reason is that we are interested in having tens of megabit per second. So it is a natural choice that we want to optimize the data transmitter part as much as we can and choose the minimal complexity in terms of circuit implementation. And in fact, it's a switching VCO. This fact means that the overlap between the voltage waveform and the current waveform is minimal, and we can get a very excellent power efficiency out of the circuit, close to 90%. But now that we have the power oscillator, the question is that how we want to conduct wireless communication. Then the first approach is to directly use the data in order to switch two switches at the source of the power oscillator circuit in order to connect and disconnect the circuit to the supply line. In this configuration, whenever the data is 1 and we are transmitting symbol of 1, we are activating the power oscillator for the entire time, and we have oscillation and the power is delivered to the antenna. The benefit of this approach is that the transition of the waveform is so smooth, and we are not ending up with a very large occupied bandwidth. But on the other hand, consider that we are keeping the power oscillator a very power-hungry block active for the entire time, and certainly is not power efficient. An alternative to this problem is to use the trigger signal and pass it through an edge detection circuit. The edge detection circuit recognizes the rising edge, and upon the detection, it only activates the switches for a very short period of time that is fixed, and we call it as Tm. Since this time is fixed and constant, we expect that the average power consumption of the data transmitter would be a scale if we increase the bit period. And in fact, you can formalize that as this equation where Tm is the fixed time, Ts is your simple period, and Po is the power consumption of the Po. So this fact means that if your data rate is low enough, essentially we can lower the power consumption of your TX module and will enable even continuous operation, having only 100 microwatt of available power. To just evaluate all of these concepts and ideas, technology, and this is the first and the only system for medical application that features a fully on-chip integration. No off-chip antennas, no crystal oscillator, and even no off-chip cap for storing the energy. We use this in vitro setup in order to characterize the performance, where the chip is mounted on a printed circuit board covered by a 1 centimeter thick chicken breast. The power transmitting coil, the green shape here, which the detail of that is shown here, is located at the 12 millimeter distance from the chip, and an ultra wideband monopole antenna is located at the 15 centimeter distance from the chip. So the performance results are very interesting, and we observed that if we fix the data rate to 100 megabit per second and configure the data transmitter in OOK modulation scheme, the system is capable of compensating for the power loss in the power transmission link by adjusting its duty cycle. Moving from top to bottom, you see that the power is degraded from 25 dBm to 23 dBm, which certainly can happen if you are dealing with practical implants because of the movement and formation of scar tissues and tissue variation. But fortunately, the system can adjust for that by increasing the charging time. On the right side, we have the performance for the ultra wideband case. Here, the transmitted power level for the wireless link is fixed to 25 dBm, but this time we are sweeping the data rate from 150 megabit per second down to 40 megabit per second. And this is very interesting because consider this, at 40 megabit per second, you are achieving a continuous operation. Just let's overview what we have here. We have only 25 dBm of wireless power. We have no off-chip component, fully on-chip integration, and we are conducting wireless communication with a 40 megabit per second rate, which is more than enough to support hundreds of recording sites. Same results for the data receiver was achieved when we evaluated the performance. The data receiver was able to recover the data, the downlink data pattern, and the recovered data here closely follows the original data pattern with a very high fidelity and high reliability. So overall, we were able to get the maximum data rate of 150 megabit per second for the transmitter and 2.5 megabit per second for the receiver, but the energy efficiency values are significantly high, 4.70 picojoule per bit and 1 picojoule per bit on the receiver end. So far we have a very reliable solution for conducting wireless power delivery and data communication, but of course, the purpose is incomplete if we don't talk about the recording and analog front end. One of the applications that I started from the beginning was neural application and coming up with complex functions in the human brain. For that specific purpose, neuroscientists are interested in action potentials, which carry energy in the frequency range of 200 Hertz to 5 kilohertz. The action potentials have amplitude up to 100 microvolts, and it is shown that the desired accuracy in terms of digitization is believed to be between 8 to 9 bits. 8 to 9 bits effective number of bits, which is related to signal to noise and distortion ratio of the recovered signal, depending on how you want to view that. So in our purpose, therefore, we targeted a 10 bits digitization accuracy in order to have some margin also to satisfy this 8 to 9 bit required level. Building upon a previous platform, which was wirelessly powered transceiver, we fabricated a new chip that included an array of 2x2 recording front ends, plus a clock recovery system that was designed with the receiver circuit as well. We also have a parallel input and serial output register in order to load the data from all channels and pass them to the transmitter for conducting the wireless communication. For the sake of the time, today I'm going to only focus on the recording front end and skip the clock recovery part and the memory part for later. So here is the circuit implementation of the recording front end, where you see we have a low noise amplifier in order to amplify the 100 microvolt signals to 1 volt, which is the operating operating voltage of our system. And the LNA is followed by a buffer, which is responsible for driving the capacitive input of the SAR ADC. The ADC has 10 bits of digital output, and it requires 11 cycles for one conversion. And since we are interested in action potentials that have frequency components up to 5 kilohertz, we want to stick to the Nyquist rate, and we are targeting at least 10 kilosample per second, which means that the ADC is driven by a 110 kilohertz signal, and this clock signal is provided by the clock recovery circuit as well. The highlight of the measured result for the recording front end I'm going to report, we observed that the LNA and the analog buffer were able to provide a voltage gain of up to 59.6 dB. And this block showed a frequency response as shown in this slide. We have a low cutoff frequency and a high cutoff frequency, which is well defined if we are targeting neural application bandwidths of up to 5 kilohertz. But most importantly, we observed that although this block only consumes 4.1 microwatt per channel, it can guarantee an excellent reliability for the recorded signal. It shows only 3.6 microvolt RMS input referred noise, which is well below the background noise that we already have for brain applications. And also the total harmonic distortion is less than 1%, which means that the recorded signal is extremely linear and very reliable. Finally, the ADC also was characterized, and during the measurement, we saw that it can achieve an effective number of bits of 9.3, which is the equivalent number of having signal to noise distortion ratio of 57.76 dB. Considering that this is only consuming 256 nanowatt for the entire ADC operation, we believe that this ADC is the most power efficient ADC that has been reported and is certainly appropriate for the use in power limited applications such as biomedical implants. Just to show the highlights of this design, this is the first and the only work for medical application that features fully on-chip integration, and the entire volume of the system is only 1.6 millimeter cubic. In terms of technical specs, we have improved the state of the art for the integration capability by a factor of 7. And for the transmitter side, we are improving the energy efficiency by 2.3-fold. And on the receiver side, we are improving by a 50-fold. Considering that all of these is done in a millimeter-sized form factor, this is the only and the most reliable solution in order to realize the future distributed sensor networks that heavily rely on small implants. But this is not the end, and we are not still done. In fact, I demonstrated in this talk that how we can enable one individual recording site to conduct wireless power delivery and data communication. But we are still far away from realizing a practical system for clinical use. The most obvious reason is that we are only having one recording site at this point. We want to stick to a distributed sensor network in order to improve the spatial-temporal resolution of the recorded signals. So I'm going to work on the network configuration of these chips for future research, and hopefully I can get there. Also, I want to point out to another domain, which is Internet of Things, that can greatly benefit from the development of low-cost and small sensors that are capable of conducting wireless power delivery, and they can conduct efficient communication. Despite the fact that IoT seems very different from medical application, but the challenges that hardware developers are dealing with in this domain are very similar to medical applications that we cover. You see that even the most power efficient protocols that are being used, they are still power hungry. And as a result, the battery life is very limited. And also these cannot be sufficient in order to power it with a wirelessly powered and energy harvesting approach. Therefore, my goal is to take these efforts further and apply the concept and the application of power efficient wirelessly powered sensor nodes jointly to the domain of IoT and medical implants and tackle the hardware related problems. Also, another important goal that I have is to explore the opportunities offered by a network of these sensors. If we have a network of sensors, we can realize many complex functions and many complex tasks. Few examples are overcoming pass loss and achieving the higher aggregated data rate when you're dealing with sensing systems. A very simple example and the initial efforts that we had on using the power of networks was published in IEEE sensor journals, where we are using a network of wirelessly powered sensors and using an external RF signal in order to synchronize the operation of distributed nodes all together. If we can guarantee that all of these sensors can reflect signals back using the same phase and the same frequency, then we will observe a factor of n improvement in the received power, which is equivalent to increasing the power level by a factor of n squared. Just to show the feasibility of this idea, we used another microchip that we designed, but this time with an injection locked power oscillator. The injection locked power oscillator features another antenna on the gate of this current source that guarantees that the phase and the frequency of the operation of the power oscillator is well controlled. By doing that, we came up with this measurement result in the lab, where you can see an array of 2x2 sensor nodes, and an external RF link was used for wireless power delivery, plus providing a reference signal for synchronization. The reflected signals were picked up by a different antenna here and were processed, and the result was very promising. In fact, on the left side, you see that what we observed in absence of the reference signal, we see 4 distinguished tones, and each tone has a power level close to -48 dBm. In the next scenario, we activated the reference signal, and all of these tones merged together, unified their frequency, and we observed a power level improvement by 13 dB, very close to the theoretical expectation that we had. Another direction that I envision for the future of wireless sensors is adding the processing capability and adding the low power processing to the sensor. An example is shown here. This application specifically is for wound monitoring purposes, where the patient is wearing a wearable patch on the wound tissue. So this smart patch is capable of conducting wireless communication, but more importantly, it is also capable of running some basic classification algorithms such as SVM and clustering algorithms. And by doing that, we showed in this initial study that you can distinguish between different types of wound and characterize different stages of healing. So this example greatly shows the important roles that smart sensors that can play for future point of care application and saving many unnecessary long waiting time in the lab and improving the general and overall quality of treatment. Just to summarize the roadmap of the future wireless systems developed by power efficient communication, I am planning to leverage the advancement in CMOS technology and integration technology in order to add new features and capabilities to the wireless systems. The application can range from neural interfaces where we have recording and stimulation, and we can also have sensing. One example I showed electrical sensing, but that is not certainly the only option. We can have different mechanisms in order to sense different biomarkers and environmental parameters. I'm planning to apply this low cost and power efficient connectivity problem to further improve the challenges and obstacles in the domain of IoT and medical implants. And certainly one direction that I'm planning to follow is exploring different and alternative sources of energy for enabling energy harvesting applications in general. I covered electromagnetic waves here, but depending on the application, we may end up with another source of energy that is optimal for us. Finally, I also envision that by utilizing the power of networks, we can shift our focus from looking at one individual recording site or stimulation site to a network of distributed nodes. And it also will enable an unprecedented opportunities for future smart sensings. So overall, all of these efforts, I believe, will lead to pushing us toward a new paradigm shift in terms of sensing and communication, where these two tasks can be viewed as one individual goal for the design purposes. Finally, I want to thank all of these amazing people that I had the opportunity to collaborate with during the course of my research. And I want to thank the funding agencies for supporting my research. And at the end, I want to thank you for attending this talk, and I'll be happy to answer any question you might have.
Okay. Wow. Thank you so much for such great talk. So many fascinating research directions. So I'm going to open up the floor for questions from the audience. If you have any questions, if you can raise your hand so that we can unmute you so that you can ask your question. I'm just unfamiliar with this feature myself, so I don't know if anybody's raising their hand and I don't see it, or but yeah, while I try to figure that out, I will maybe ask you a question. So could you comment on like the antenna fabrication, you know, and how it's integrated with your CMOS chip? Is this something that's like trivial to do, or is it non-trivial? And is there like a way to optimize this? You know, things like also like position and alignment with respect to the you know, the transmitter. If you could comment more on that, that would be great.
Yeah, sure. Thank you, and actually that's a very great question. And one of the very big challenges that we were dealing with was the antenna integration itself. So you have seen basically conventional designs where the antenna is viewed as a completely different design problem from the circuit design. But since we are targeting very millimeter-sized application, the integration of the antenna was one of the most important parts that we were dealing with. Therefore, we basically came up with very simple and low profile antenna types. And traditionally, we know that for power transmission, people are using coils in low megahertz frequency range, primarily ISM bands. But as I said in my talk, if we increase the operating frequency to hundreds of megahertz, that was presenting a new opportunity in order to shrink the size of the power receiving coil to millimeter size. So we did that. We moved forward to 250 megahertz. but still integrating the antenna on the CMOS design still is not as efficient as a standalone antenna fabricated on a very low permittivity substrate. So just to answer your question, I believe that there is still a lot of room for improving the performance of the antenna. One very simple example is that instead of using bulk process, we can go with SOI process, where the substrate has much smaller conductivity, and therefore the antenna has a much better performance in terms of efficiency. Also, there are other directions that we can follow that have not been explored yet, because nowadays metamaterials also are emerging as one approach in order to realize electromagnetic characteristics. So if we can just integrate those type of design into CMOS technology, that will also open up for a better performing antennas as well.
I see. Thank you. So there's a question in the chat box. One of the students says, "Hi, Dr. Rahmani. Can you explain what kinds of sensors you used in this design, and how can these sensors be combined and integrated in an IoT network?"
Yeah. So the sensing part that I described today was mostly focused on recording the action potentials, and the approach was based on an electrical sensing, where we had this low noise amplifier. This is a completely different configuration from typical LNAs you see in RF applications. This is an analog low noise amplifier, primarily used for gain and input referred noise. So in terms of sensing, if I wanna go back to the visionary example that I showed at the beginning, yeah, this is the perfect example. You can see that your integrated SoC is sitting on top of an array of electrodes. So these electrodes are sensing the electrical activity from neurons that are in their close proximity, but we are responsible for basically amplifying the signal and bringing the level up in a way that they are sufficient for being digitized. So this is the main sensing approach that I presented in this talk. But back to your point about future opportunities and IoT application, it primarily depends on which parameter that you are dealing with. We can talk about temperature, humidity sensors, EM sensors, and so many other things. But again, depending on the application, you may want to decide. You may have electrical sensing systems for, again, sensing the temperature, or you can have MEMS for basically measuring the acceleration and gravity and so other. So the long answer to your question is primarily depending on the application.
I see. Okay. So one question I had, again, related to the antenna. I know when you do everything in CMOS, you're able to make things really small. Would there be any benefit to having like a quasi integrated solution where, if you had a little bit more flexibility in the size of your implant, if you could make certain things like antennas off chip and then, the rest of it on chip, would that help or no?
Yeah. That is certainly some topic that can be further improved because, as I said, integrating the antenna on the same silicon chip is primarily challenging because of the substrate loss that you have. If you can guarantee that you can come up with a very compact structure, certainly we can get better efficiency from the antenna. But have this in mind that also adding those type of antennas require post-processing. you have to connect your integrated circuits with the antenna, either using bond wires or going with a bump process. It requires post-process. But if you have everything on the same chip, post-processing free and yeah, nothing else. It primarily saves a lot of cost, but for medical applications, cost may not be a big concern. But certainly for IoT, on-chip integration has a lot of advantages in order to save costs.
Yeah, that makes sense. So actually following along that theme, so medical devices, what do you see as the bottleneck to getting one of these devices into a medical device?
Yeah, that's also a very interesting challenge that is facing for practical cases. So I would say powering is the primary concern that I can envision right now, because as I also said in the talk, since these systems are millimeter sized, you have to have alignment and polarity matching between your transmitter and receiver to a very good extent. So that can be easily disturbed if you are going into clinical applications, because you never know with how much accuracy you can control the position of your antenna. And in fact, this is also a very challenging problem in terms of research activities in antenna and propagation society, that people are trying so hard to address this question, how they can come up with a generic type of antenna that is not very sensitive to the misalignment. But I would say powering certainly is the most limiting factor so far.
Okay. Yeah, that makes a lot of sense. Okay, so we are just at 11 o'clock. I think that probably doesn't give us time for more questions, but really wanted to thank you, Dr. Rahmani, for being with us today and presenting your very exciting work for us. We wish you the best of luck. Thanks again, and we look forward, hopefully, after the pandemic ends, maybe to have you on campus one day. and
yeah,
so,
it would be my pleasure actually to visit the campus and the amazing people there.
Thank you so much. So have a great day, and thank you everybody for attending.
Mm-hmm. Yeah, and at the end, I want to say that I know that because of the power outage that they had, like we lost also a couple of more minutes. But if you do have any further question, just feel free to send me an email. I believe my contact was shared, so I'm happy to answer any question you might have.
Thank you so much.
Mm-hmm. Okay.
Have a great day.
Thanks. You too.
Thanks. Bye-bye.